Yeah, okay. So now the corollary, right? The corollary is like immediate, right? Is basically if I have a set that's simply connected, a region that's simply connected, then, you know, every closed curve is homologous to zero. That was the definition of simply connected. Well, okay, not the definition, but that proposition showed that it was equivalent to the definition. And so for sure, Cauchy's theorem holds on any simply connected region, right? And so in particular, it holds in the disk, for example, right? So this implies right away Cauchy's theorem on a disk, right? So right away implies Cauchy's theorem on a disk. Okay. So now let's prove Cauchy's theorem. Okay. Hopefully we'll be able to do it. I should say before proving. Okay, so maybe before proving Cauchy's theorem, let me just say a word about some implications of it, right? One implication of it that you get almost, I mean, not quite right away, but it's the fact that if I have right, so if I have a function that is right, if I have a function that's analytic in right, so maybe let me just write that, right? So some implications, and then you'll see this in exercise classes with a bit more right, because I claim that, right, for local and smoothness properties of analytic functions, you know, the Cauchy theorem on the disk was already enough. This Cauchy theorem gives us more global properties, right? So for example, it gives us things like this, like if, you know, gamma is simply connected. I won't prove this. Maybe I'll ask I'll ask for this to be, you know, discussed during the exercise sessions. Is simply connected, right? And F is analytic, right? Then actually F has to have a primitive. F has a primitive. Right. So why? Because I mean, the proof of this basically is, you know, we know that the integrals on closed curves are zero in a region that's simply connected. And so basically we know that integrals don't depend on the path. And when integrals don't depend on the path, you can define a primitive just by taking the path from, you fix a point and you take the path to another point, and, you know, just take the integral to be the primitive. And basically because of that, we saw this equivalence between the function having a primitive and the integration not being path independent. And so you can define a primitive in any region that's simply connected. And in particular, this implies a lot of implications of this. And you'll see this in the exercise session, right? Is that if F in a simply connected region, right, is analytic, and F of Z is non-zero for any Z in the region, and the region is simply connected, right? Then one can define, right? One can define an analytic range of logarithm of F of Z and, to say, square roots of Z and so on. Right? Why? Because, I mean, it's really not that hard, but it takes a second to do, right? But what is the reason? The reason is that, and you'll see this in exercise classes, is that basically, you know, F prime over F has a primitive in in omega, right? Because it's analytic, since f has no zero, this has a primitive in omega, and so for that reason, you can turns out that you can define the log and so on by using the primitive of this function. Okay, so you'll see some of this in the exercise classes, right? And if you think about what's happening with the log and the square root and so on, right? The issue, say for example, with the log, right, was that when you loop around, right? So the log was the primitive, you know, has issues at zero, and it would be the primitive of a function that has issues at zero, right? And so you can, when you go around, you add up this 2 pi I, right? So when you go around in the log, the argument grows by 2 pi, because you get something like the angle, and the angle goes from 0 all the way to 2 pi, and this is the issue of why one has trouble defining the log, right? But clearly it's not, if I want to define the log of a function, if 0 is not in the set, right? If 0 is not, then the region in which I'm doing this is not simply connected. And as long as we have something that's simply connected, right, then this problem won't arise. Okay, so I'm going very, very high level, but this will be discussed in the exercise classes. Okay, I saw there's something in the chat, but I didn't see. Okay. Right, and we saw that if we had, if we took away this part, for example, there would be no trouble defining the log and so on. This is a much nicer, more general version of all of that. Okay, so but the message I wanna give here is that, right, this form of Cauchy's theorem allows us to say more global things, right? This is now more of a global statement, right? That we can define something like the log of a function or the nth root or something in all of the region, right? Analytic, meaning single valued, and right, we don't have to deal with taking branching points and things like this. Okay, so let's prove Cauchy's theorem basically in the last 20 minutes, because basically, we've done we've done now. I mean, the proof is basically the same as constructing those squares. I mean, more or less. So let's do it. Maybe another way of thinking about Cauchy's theorem is that it's saying that the only issue that can arise from integrating a function on a closed curve in a region is basically the issues that arise with functions looking like 1 over z minus a. Right? Because if there is such a function, 1 over z minus a, that doesn't integrate to 0, right? This basically means that there is a winding number that's not 0, right? And so the curve is not homologous to 0. And so basically, Cauchy's theorem is saying, in order to check if the integrals are 0, all you need to check is basically functions of the form 1 over z minus a. And in a way, the calculus of residues and so on makes this a lot more precise. But we'll get there. Okay. Okay, so let's do the proof of Cauchy's theorem. Okay, so proof. Okay, so let's start with our objects just to put everything, put our minds in the right place. So we have a region, and we have gamma closed curve. Moreover, we have that the winding number of gamma with respect to a is 0 for all a's in the complement of omega. Okay, and the goal, right? It's good to write the goal just so that we all follow the proof. Okay, and the goal, and I should say an F analytic, right? F defined in omega C analytic, right? So the goal is to show that the integral around gamma of f c dz is equal to 0. Okay, right? So this is what we have, and this is what we want. Okay. So let's say that, okay, let's start with bounded, because I'm going to, right, the strategy will be again to fill the space with squares and then say something about these squares. And so for that reason, I'm going to start with bounded omega. Right, just because if I start with bounded omega, then things are a bit are a bit nicer. But let's suppose that I have bounded omega, and then in the end I'll just show, because then I have a finite number of squares and I don't have issues there. And then I'll just show that even if omega is not finite, we can still do it, reduced to the case in which it's finite. Okay, so we take, right, we do the same strategy. So we take delta bigger than 0 and fill the space with squares Q J of side length with side length delta. Okay, and now let me take QJ's, right? J in a set J to be the ones, the squares right? That the squares in omega. Okay, so basically J, the big J is equal to the set of little j such that Qj is inside omega. Okay, so maybe I should draw a picture. Let me draw a picture here. Some set omega, and now I'm trying to draw a bunch of squares. Maybe I should have my omega have, not be simply connected. Let's say there's a hole here. Right, and so on and so forth. I'm picking the ones that are completely inside, which in this case are just these three. No, this two even. Okay, just two. Okay, so these are the ones that are completely inside. Right, because it's bounded, right? Because I started with bounded things. Then I have that J is finite. Right? The set of squares I'm picking is finite. Of course, I want to pick smaller and smaller squares to see more, but this is the construction you should have in mind. Okay. Okay, now the idea is we're going to take an approximation, right? So let me write maybe idea. Idea is take an approximation to the boundary of of omega, and the approximation we're going to take, right, is just we're going to take the boundary of that set of the squares, right? So we define this to be the sum for all j's in the set J of the boundary of the QJs, right? So here this set is just this, right? So this would be my big gamma of delta. And of course, if I start making my square smaller, let's say I make them half the size, right? Then I start seeing, more interesting things. I start maybe having, this starts being, I don't know, maybe something like this. Right? I start having a better approximation, still looking like polygon lines, but a better approximation of my set. Right? The smaller the delta is, the better and better approximation I get of my set. Okay? And now I want to define the interior of this, right? So I'm approximating the boundary. I want to now define the interior, right? Because it's a set, let's say. Okay, so now I have, I'm going to define omega delta to be equal to the interior of the union of these J's. Okay, is the construction clear? Hey, I realize the picture might not be great, right? But if I have, maybe let me draw another one. Right, then basically you can imagine taking maybe something like this. Okay, and so these are my little squares. This is my region inside, right? The interior of all this rectangular shape, or like little net shape, is omega delta, and this boundary is now a gamma of delta. Okay, so this is the construction. Now, of course, now let's take our objects. So now this is a closed curve. In omega, for sure, there exists delta bigger than 0 small enough, right, such that the curve is actually inside the approximation, right? Because the approximation gets finer and finer and finer, the curve is fixed, so for sure at some point that will be. So let's take such a delta, right? Take such delta. Okay, so now I have to erase. Okay, so now let's take a point. Okay, so what's going to be the strategy? Right, the strategy will be to show that any point in this curve, any point in this boundary needs to have winding number that is 0 with respect to gamma, right? So gamma will be somewhere inside, let's say here. The strategy will be to show that any point in this boundary needs to have winding number 0 with gamma. Okay, so let's do that. So let's take, right, so in particular, this is a point that is in omega, but not in this approximation omega delta. So we're going to show that all these points have a winding number 0. Okay, so let's take C. Okay, let's take C to be an element of omega minus omega delta, right? Or I mean, I've been using the notation set minus like this. Okay, so it belongs, right? It must belong to a Q, say K, for K not in J, right? Because even if it's in the boundary, right, it must belong to another square, right? Maybe it's in the boundary of, say, this square, but it must be in the boundary of also one of the other squares, right? So it must be in a Q for Q not being in J. Okay. So there exists. Let me go back to the white chalk. So now the strategy will be to say, well, if it's in a Q that, okay, this can't be the right picture, right? So if I have a point who's not if I have a point who's not in omega delta, then it must be inside one of the squares that is not inside omega, right? Because otherwise it would have been included. Okay, so it must be, and even if it's in the boundary of one, it must be in the boundary of one outside. So it must be inside of a Q that's not in, that wasn't included here, right? That wasn't inside omega, and so they must exist, right? And so maybe I should say it like this. So QK is not inside omega, and so there exists some C0 in, like, outside omega, such that C0 is inside my QK. Okay. Okay, and so right, and so I can connect C and C0 with a line segment, right? That doesn't intersect the interior of the other squares, right? That doesn't intersect. Right, the interior of the other squares, right? Because this line segment is completely inside that one square. And so in particular, it also doesn't intersect the curve gamma. This means that the winding number of gamma on Xi needs to be equal to the winding number of gamma on Xi0, right? Because I can link them. They're in the same connected component of the, right, they're in the same connected component of the regions, the region delimited, or they're in the same connected region that is determined by the curve gamma. And we know that this is zero by hypothesis, right? Because this point, C0, is not in omega. And so this follows from the fact that gamma is zero modulo omega. Okay, let's see, questions. Okay, so the curve can't touch the boundary of omega, right? Omega is a region. It's right. Omega is a region, so it's open. So the curve, the boundary isn't inside, right? So when this is inside omega, it cannot touch the boundary. Okay, more questions. Right, so it's a closed curve in the interior of omega. I mean, omega is an open set, right? So its interior is just it's just a set. Okay, other questions? Yeah, and so but therefore I can approximate with delta small enough such that I can capture gamma also inside this smaller region, this gamma of delta, but this smaller region is made of like vertical, the boundary is made of vertical and horizontal lines, and so right, it's a lot. It will be easier to understand. Okay, so is this clear? Right, so what am I doing? I'm saying take a point here. There is another point. There is another point over here. Because n of gamma and this point is zero, that must be true also for the green one. And so I'm already starting to be able to have points that are right in omega, and in particular, I can right. In particular, because the boundary is not in omega delta, the points in this boundary, let me see if right, the points here in this boundary will also have winding number 0, right? So now not only do I know that the winding number of my curve, because it's homologous to 0, is 0 outside of omega, but I was able to push this inside all the way to the boundary of this set that I understand better. Okay, so this means in particular, okay, I have to take, I think, like 3 more minutes to finish the proof. I mean, we're almost done. Sorry for the issue with the microphone. We're like almost done. It doesn't look like it, but we're actually quite close to done. Okay, so in particular, right, the winding number for any point here is 0. So in particular, we just proved that for all C in this approximation to the boundary, the winding number of the curve to the point is 0. Okay, so now the trick is to use the Cauchy integral formula and just swap order of integration, and we're done. Right? So let's do this. So let's take f, right? F is analytic. Okay. Let's take z inside the interior of one of these q's, right? For some qj. Okay. So because now z is in the interior of a qj, I can use Cauchy, right? I can use the Cauchy integral formula, right? And this qj is completely inside omega. I can use Cauchy integral formula in the boundary of this, right? Because this is just, a square inside that region. I can definitely use it here. And so what do I get? I get that, if I take 1 over 2 pi I, right, of the integral around the boundary of qj of just fc minus xc minus z dxc, right? This is equal to, let's say that this is over some j0, right? This is equal to what? This is equal to f of z times the winding number of this curve around the point z, right? So in particular, this is equal to right, by Cauchy integral formula, this is the same as, right, the winding number of this curve around the point z times f of z, but the winding number is exactly 1 if j is the same as j0 and 0 otherwise. So this is equal to f of z, right? If z is equal, if j is equal to j0, right? If I'm integrating around the right square, right? And this is 0 otherwise. Okay, so this means in particular that I can just take the sum, right? Okay, let me do this. So if I take 1 over 2 pi I, the integral over that region, right? Maybe let me write it over here. Okay, 3 more minutes. Sorry for the extra time. So if you have to go, I'll post a record. I'll try to post a recording quickly so that you can watch it after. But just sorry, I try very hard not to go over time, but here to reconstruct this all again on Friday would spend a lot of time, right? So now I can take 1 over 2 pi I, right? Integral over the whole, right? What is this? This, remember, this is equal to the sum j's in j, right, of the boundary of qj's, right? F c minus z dxc, right? So what is this equal to, right? This will be equal to the sum over all j's of this, right? But then j is exactly equal to j0 exactly once, and it's equal to, right? It's equal to j0 exactly once, and so you get some of fz summed exactly once, right? So this is definitely true for z right? This is true for all z in the interior of qj for some j. Okay, right? Because on this side I just get the sum over this over all j's, and here if I sum this over all j's, I get 0 a bunch of times, and I get f of z exactly once. Okay. Now, what is the problem? Like, okay, so but I want this to be true for all, also in the boundaries of the QJs, right? I want this statement to be true also in these boundaries. But by continuity, right? Because, you know, right, both f of z and this integral are continuous, right? Inside that the smaller region, this holds, right? So let's say, right, holds for all z. Okay, so if your point z is inside the interior of one of the squares, you are done just by summing that. If your point z is in the boundary in between two of these squares, right, like you have maybe one and maybe two, for the z's here and here is fine. For the z in the middle, it needs to hold by continuity, right? Because both this and this are continuous functions of z. They match in, right, in the inside the squares, they also need to match on the boundary. Okay, so now we're done, right? Because now we have that this is z for all elements z in this smaller region, and now we just take the integral and we replace f of z by that, right? So now, okay, now we are done. Why? Because just take your curve gamma, right? Remember that we set it up so that gamma would be inside this set. So now what is the integral? The integral of gamma fz dz, right? We can just replace by that formula because this formula holds for any z in omega delta. So this is equal to the integral over gamma of now, right? 1 over, say, 1 over 2 pi I, the integral over this boundary of f c c minus z dx dz, right? So this formula holds because this holds in any omega delta, right? Just because these are all continuous, right? These are all like they're all very nice functions and they're all continuous functions, and you know the gamma doesn't intersect that, so there's no issues here, right? These are continuous functions of both variables and so on, so there's no problem in swapping the order of integration. And so if I swap the order of integration, I get the integral over this curve of now, okay, let's say delta 1 over 2 pi I f c over c minus z. Now first dz and then dc. Okay, now I can move fc to the other side, right? So I get, and I can move 1 over 2 pi also outside. So I get integral, right, over this region of fc. Okay, now what do I have? I have 1 over 2 pi I integral around the curve of 1 over c minus z dz, this time this dc, right? But what is this, right? This is exactly minus the winding number, right? If I swap the z with, like I just put a minus sign, this would swap, is exactly minus the winding number of the curve with respect to the point c. But we just showed that this is 0 because we showed for any c in the boundary of that set, right, this approximation to the boundary, this is 0, right? And so the whole integral needs to be 0, right? And we're done. right? And so okay, and we are done. Okay, sorry for taking a few extra minutes. Next on Friday, I'll describe a little of other ways to prove Cauchy's theorem, because there's other different approaches that are not as based on winding numbers. And I'm happy to stick around and answer any questions if anything is not clear. Okay, sorry again for the extra 9 minutes and the issue with the microphone, so on, but hopefully the proof is clear. Ah, good point about unbounded omega. Thank you. Keeping me honest. Thank you. Okay. Yeah. Good point. I was almost going to forget that. Great. Thank you. It's in a rush without looking at my notes is easy to forget. Okay. Yeah. Okay. Let me say that. So what if omega is unbounded? So that's easy actually, because let's say that this is a closed curve in omega, right? Then take R large enough so that so the disk of, say, radius R, so what I mean by this is all points Z such that Z is smaller than R, such that this is so that the curve is also inside this disk. Okay, so I've just, if omega, even if omega is infinite, right, let's say, omega is infinite, it goes up continuous, then if I take my curve gamma, I'm just going to draw also a circle and take the disk, and now take omega prime to be the intersection of omega and this disk. Right? What I'll just show is that if omega was congruent to 0 mod omega, then gamma is also congruent to 0 mod omega prime, right? The reverse is always true. When something is congruent to 0 in a set, is always congruent to 0 in a bigger set, but going to a smaller set is not always true, right? But let's show that this is the case. So take A in the complement of omega prime, then there's two options. One, A is in the complement of omega, and so then, this is true by hypothesis. Or two, A is inside the complement of the complement of the disk, and then because it's outside, because we've seen this already. If we have a disk that includes a curve, then any point outside of that disk has winding number 0. Is also 0, right? By simply connectedness of the disk, or just I think we even proved this directly, right? And then after this, just use proof on omega prime, right? So there's only, if a curve is homologous to 0 in a region, it's always homologous to 0 in a subregion that's bounded, and just use the proof for that subregion that's bounded. Okay, thanks so much for bringing up the unbounded. I had completely forgotten. Yeah. Okay, and I'll stick around in case there's any questions.